Today we're talking about solving absolute value inequalities. We just recently talked about the absolute value equations, and there's a lot of similarities to these, but we also have to keep in mind with these inequalities some of the things that we'll have to keep an eye on for our graphing and understanding which types of graphs to use, whether we're using the ands or the ors. So when we look at an inequality that has a less than, or also could be the less than or equal to, these are going to be our and statements. Okay, so let's just make sure we understand that. So ands are anything that are the less thans. Kind of rhymes if you kind of say it that way, less than, and the and statements come from any of our inequalities with the absolute values that are less than or equal to. On the other side of that, when I look at the inequalities that are greater or could be greater than or equal to, we are looking at the or statements. And this one, I think, if I write this out, it's greater is the or statements. So if I have a absolute value that is now isolated, and that's kind of the key thing as we go further here. Remember, we have to isolate the absolute value expression before we do too much. Once I've isolated the absolute value expression, if it's a less than or equal to, it's now going to be an and statement. So we're looking for the intersection of our solution sets. If it's a greater than or equal to, it is greater, so it's an or. And that will help us know if we're using an and statement or an or statement. So I'm going to skip over this next piece because this next piece is just the kind of mathematical thing of it, but I'm going to get right to how we would solve one of these. Okay, looking at this first one, and obviously this text did not come through on the video. This symbol here, which is actually the pound symbol for the English currency of money, is supposed to be less than or equal to. So when we solve these absolute value inequalities, all right, there's a couple of things we have to remind ourselves of. So just like when we did the equations, we have to have the absolute value expression isolated. So it's all by itself. There's nothing else kind of on that same side. So then what we do is we're going to take that same idea, is we're going to take that expression out, so the x plus 7, and we're going to keep it less than or equal to the positive 2. And this is where it's going to be a little bit different. Because it's a less than or equal to, we are definitely doing an and statement. Then we're going to take that same x plus 7, just like we did with the equations, to the negative 2. But one of the bigger differences here for these versus the equations is we're going to take that less than or equal to and also reverse it. So when we go to the negative, you have to also reverse your inequality symbol. So we start out with a less than or equal to, it has to reverse to a greater than or equal to when I do the negative 2 for that next statement. Once we have this, then we're just solving. So then I would say subtract 7, and I'm going to get x is less than or equal to negative 5. And keep that in mind because that's important for the graph. I'm going to subtract 7. X is greater than or equal to negative 9. So once I have that, being an and statement, really what I should do is put the x down the middle. The lower or least amount, or the least number, is negative 9. Negative 5 is the highest, so they really should go in that order. X is less than or equal to negative 5. It's greater or equal to negative 9. So that would be my best answer as a compound inequality. And then to graph this, my number line, I'm just going to kind of focus here on negative 9, negative 7, negative 5. We are less than or equal to, so in big bold circle at negative 5, coming this way. We are greater than or equal to, so a big bold circle with a negative 9, greater than comes this way, so the overlapping piece would be this segment. So maybe just put one big kind of box around this so we can see that would be our answer as a compound inequality as well as the graph. So on the next one, again, we do have this isolated, so we can start looking at what we're seeing. This one does have a less than sign, so this would be an and statement. But one of the things that I want to pay attention to here is right here, less than 0. So if this was less than or equal to 0, I could go forward. If this was greater than 0, I could go forward. But this is less than 0. So that means that the right-hand side is always going to be negative. So can I have an absolute value that is negative? Well, no, because every time I do this, I'm going to have a positive come out of the absolute value. So this is one that you don't even want to do any work on. You want to be on the lookout for, and you want to say no solution, absolute value is always greater than or equal to 0. So again, if it was at least or equal to, then we could keep going. If it was greater than, we definitely could keep going. If it was equal to just 0, we could definitely keep going. But because this is less than 0, that means we can never get an answer to make that work, because once we do the absolute value symbols, it's always going to be 0 or positive, and that won't match. So here we have a new one where we're looking at solving the inequality and graph the solution. So again, you want to ask yourself, can I do this one? And yes, these are greater than or equal to a positive number, so I can definitely do this one. So we're just going to say c minus 1 is greater than or equal to 5. This is an or statement because it is greater or equal to. So then I would do the c minus 1 again, and remember to reverse the inequality and go negative. And then we're just adding 1 to both sides to get c is greater than or equal to 6, or add 1 to both sides. Adding 1 to both sides, oh, not a highlighted one, a regular one, and we're going to get c is less than or equal to negative 4. So remember, on the number line, we have an or statement. We don't need to compound those. That is actually kind of what our answer is going to just look like. So what we would have is we're going to have it is greater than or equal to the 6. So it would be heading off in the right direction, the greater than side, with the bold arrow. And also at the negative 4, heading off into the left side. And really negative 2, 0, 2, and 4 should probably be on my number line to kind of get a decent scale sitting in there. Definitely not a great stylus number line. But that would be the graph to show that we are seeing an or statement. So on the next one. So for this next one, again, I have a greater than a positive, so I just have to go ahead and start with the compound, the inequality that's greater than the 2. And then it's a greater, so it's definitely an or statement. 10 minus m, I reverse the sign to go to the negative 2. So then, this time, I'm going to subtract 10 from both sides to get negative m is less than or equal to negative 8. When I divide by the negative 1, notice that I'm doing a couple things here. Dividing by negative 1 is going to turn my numbers to m and then positive 8. But then remember that it's also going to reverse my symbol in the middle to become now less than or equal to 8. Or, the same idea here. When I subtract my 10, I'm going to get negative m is less than or equal to negative 12. When I divide by the -1, it's now greater than or equal to positive 12. Okay, so it's important that you remember all the rules that we used in the equation still work. When I multiply or divide by a negative, the sign reverses. Again, being an OR statement, I'm going to have 8, 10, 12, greater than or equal to 12 goes this way, and less than or equal to 8, bold and closed circle would go that way to give me my solution for this one. Now on the next one. So the next one obviously has a little more to it now. So we have a couple of things that have to happen first. So we got to be careful on these. We have to wait until we have everything figured out as far as isolating that expression first. Once we've done that, then we can analyze the rest of it like we've been doing. So on this one, I see multiplication right here times the absolute value expression and a addition. Remember, this is not distributive property. Do not go through that with distributive property. So what I'm going to do is I'm going to first subtract 1 from both sides. That's going to leave me 4 times the absolute value of 2x minus 5 is greater than 20. Then, to move the 4, we're now dividing by 4. And that's going to leave me now the absolute value of 2x minus 5 is greater than 5. Okay. Now again, it's a gray TOR, so that means I have an OR statement. Now we have this isolation. So now I can just say 2x minus 5 is greater than 5, and 2x minus 5 is less than negative 5. Okay, you can't forget that second one. When I put that negative to it, it has to reverse the symbol. So here I'm going to be adding 5 to both sides. I get 2x is greater than 10, which means x is greater than 5. Or I'm going to add 5 to both sides and get 2x is less than 0. And remember, we can do less than 0 when I'm outside the absolute value symbol, so I get x's are less than 0. And again, on my number line, I would just kind of put my OR statement here. I'm going to do negative 5, 0, positive 5, greater than 5 means open circle going off to the right. Less than 0 is an open circle at 0 going off to the left. And there it is, the graph with x is greater than 5 or x is less than 0 for the solution, and the graph below it showing the OR statement that looks like the two open circles going in the opposite directions there. So next what we want to talk about, and we're going to talk about this one just briefly, this is not something that we're going to spend a ton of time on, but talking about absolute deviation. This absolute deviation is a number from a given value that is the absolute value of the difference of x and another number. Basically what it really is, it's the margin of error. And you see this a lot when you talk about polls. You'll see this on surveys. You'll see that people will say that this number percentage of people prefer hand soap to hand sanitizer. And then someplace it'll say with a absolute deviation of plus or minus 3%, or a margin of error plus or minus 1.5%. And basically what it's doing is allowing for a little bit of a kind of gray area of, it's not going to maybe be 100% correct every time they give the poll, but it kind of shows you how close it is to being accurate. If you have a small margin of error, that would be a pretty good poll, because that pretty much means you're going to get about that correct number most of the time. You'll see this obviously a lot in the election time when they start talking about polling voters to find out who they think they're going to vote for. And they start saying that there's a margin of error at the bottom, and it gives you an idea of how accurate it is. The more people you talk about, you should have a smaller margin of error, hopefully, because obviously it starts to level out the averages. So in this last example, so we're talking about trying to find out what is the amount that we are willing to pay for these computers. So they're basically giving us a whole bunch of computers, and they're saying that you're willing to go at most $100 over the mean price with the absolute deviation of 100. At most 100 means it could be 100 below that average. It could mean it's 100 above that average at most. So absolute deviation would be not only above it, but also could be below it. So here's how we would just do this. So number one, you would find the mean. So we all know finding the mean. We add up all the computer prices and we divide it by the number of computers. So that comes out to be $664 for this bunch that we looked at. So basically what we're saying then is, if you are willing to pay somewhere at most $100 around that mean, that basically means you're willing to spend $564 up to $764. $100 below it and $100 above it. So then the question says, how many of the computer prices meet your condition? Well, if I look through these, 650 meets my condition, so doesn't 660. I'm not really sure why you wouldn't select the 451, even if it's not in your standard absolute deviation. It is cheapest, but that's another story. 725 fits. 750 fits barely. Again, 370 I think is a pretty good deal, except we're just focusing on this problem, and I understand that that doesn't make sense for real life. And then these two here also fit. So to answer this question, we're trying to find out how many computers. We have 6 computers that would fit that condition. I would argue that there's actually probably 8 that you would consider buying first, because you have 2 that are well below that. But as far as just with the absolute deviation of at most 100, it would be 6 computers. Hopefully this helps a little bit. More focused on the first parts up top with the absolute value inequalities. If you have any questions, please feel free to ask as soon as we have a chance to see each other, and we will talk to you again soon.